I need a touch-up. You look fine. But you're not on the
That's
screen
because,
that I'm broadcasting.
oh, okay, well, whatever. All right, so as far as doing the whiteboard, I don't know. I mean, I would put in a ticket with Classroom Technologies, or perhaps you could pull up PowerPoint or something and do a drawing, maybe. I don't know.
Oh, God. All right, I think we're just going to have to forget about whiteboard for this meeting.
Okay, so
Anyway,
record. You
anyway,
got to start recording
I
because it's
think
5:30.
I think we've got it working. Yeah. So thanks a lot, Leanne. Okay, it's 5:30. We ought to start class.
Bye.
Bye, Leanne. Thank you.
Did you record? Are you starting to? Okay, good. Okay.
Yeah, we're recording. Okay, so let's get rid of that. And let's make this a bit bigger so you can see better. So I plan to go through chapter 2 today. And the first part is just the definition of a derivative. And of course, you know that. And here's an example if you want to refresh your memory. And of course, a partial derivative is actually a whole derivative of a function of several variables in which you hold all the variables constant except one and then do the ordinary derivative with respect to that one variable. I'm sure you've all known this for years, but what is useful and maybe new to you is the notation. Namely, we often use primes to denote derivatives or dots. Dots are typically used for time derivatives, 2 dots for acceleration. And then it becomes, especially in general relativity and when dealing with vector quantities, or in various contexts, one sometimes wants to indicate that we have the kth derivative of a function. And so one writes f with k in parentheses, or the k plus l derivative with respect to the first variable k times, second variable l times, so we write f, and then the superscript is k comma l. Another notation that's common is f sub x, or f sub comma x, and that means d by dx. And if you have a triple derivative, then it's f sub xyy, and that's equivalent to f sub xyy, and that's the third derivative of f with respect to x and twice with respect to y. What's often done, especially in general relativity, is to label variables by indexes. And for example, f comma k will be the derivative. Yeah, here it's a different notation. F comma k doesn't mean the kth derivative. It means the derivative with respect to the kth variable. So f sub comma k is the partial k of f, or partial f partial xk. F comma kl is this double partial derivative. I used to be fond of this common notation, but oh goodness, there's a problem with screen sharing. What is the story here with screen sharing? I have it here as, my screen says you are screen sharing. Okay, well, some people can see it. You have to log in with your password. Boy, if somebody knows how to turn off passwords so that just people can log in without being special, let me know. By the way, if you guys want to use anonymous names like Marie Curie, that's very nice. That's cute and amusing, and everybody will be amused. We all need jokes. So if any, it's perfect. You don't need to appear as anonymous. If you want to, one of you wants to be Einstein, another one Planck, and so forth, go for it. I think that's great. Let's now get to the next topic, gradient. In the simplest case, what we have is 3 coordinates to label a point P in a 3-dimensional space. And there's a convention that was introduced by Elsevier, I think. I first saw it there. And it's to use bold-face type for 3 vectors. This, unfortunately, has become a common notation. I don't think it's a very nice notation, because you then get a screen with lots of bold-face type and just looks ugly. Anyway, and then what do you do for bold? What do you put in bold-face? Do you put only 3 vectors, or do you put in 2 vectors and 4 vectors and 9 vectors? Everything is in bold-face, and pretty soon everything's in bold-face type. I don't know. I don't like this notation. I think we need a better notation. In any case, at the moment, what we've got here is somebody's unmuted and has a cough. Let's see, how can I move this somewhere? Can I move this thing somewhere else? Let me try to, oh yeah, it's there. Okay, great. All right, that gives us more screen. Okay, so the change in a point P due to changes in the coordinates, of course, is the partial derivative of the point with respect to each of the coordinates times the change in the coordinates. And that's then a unit vector in the one direction at the point P, and in the 2 direction at the point P, and the unit vector in the 3 direction, and times D3. And well, I said a unit vector. I misspoke. It's a vector, and we don't need these to be unit vectors yet. What we do want, if we want a simple notation, is we want these vectors to be orthogonal. So, and they have specific lengths, which are hi and hk in this case here, but we want them to be orthogonal. So ei dot ek is delta ik. The orthonormal vectors are, all right, there's a typo there. That should be ej divided by hj. So, so the change in terms of these orthonormal vectors, the change is the length of the vector E1 times the orthonormal vector, the normalized vector in the direction E1 times the change in the coordinates U1, and so forth, added up for the other 2. Now, in 3-dimensional space, we have this nice cross product notation. And so what one can do is define these vectors so that EI cross EJ, the orthonormal ones, gives you EK, where we have a sign that is positive if this is a cyclic permutation of IJK. So E1 cross E2 is E3, E2 cross E3 is E1, and E3 cross E1, I think, is E2, although I've lost track now. Anyway, this epsilon IJK, of course, is the Levi-Civita symbol that we were talking about earlier. Anti-symmetry occurs over and over again in physics and mathematics, and I think in undergraduate physics classes, people don't emphasize it as much. In rectangular coordinates, everything is much simpler. The changes are dx, dy, dz. The change of the point is x hat dx, y hat dy, z hat dz. All the h's are unity. In cylindrical coordinates, though, and this is what I wanted the whiteboard for, but I couldn't figure out what I would really like to do would be to write on my iPad and produce a window here that you could see in live video. Anyway, you must know about cylindrical coordinates. The change in the point P is rho hat d rho. But on the other hand, when you change the angular coordinate phi, it's rho phi hat d phi. And when you change the z coordinates, just z hat dz. By the way, this sense in which phi is changing is it's the right-hand rule. So if you if you hold your right hand and have your thumb pointing up, then the angle phi is increasing the way your fingers point. Here the scale factors are 1 rho and 1. In spherical coordinates, the change in the point is r hat dr, r theta hat d theta. This is the polar angle from the top. And then the angle going this way is r sine theta phi hat d phi. It's r sine theta because if this is the z-axis and the angle theta is like that, then when you change phi, you move according to this moment arm, which is r times the sine of this angle. So the scale factors are 1 r and r sine theta. And to summarize those equations that we went through, dp is that. Now the gradient is defined in terms of this notation. And I think I can make this a little bit bigger and just do that. Okay, so the gradient of a scalar function is defined so that the dot product of the gradient with the change in the point P is the change in the function when you change the coordinates by dp. So the gradient of f dotted into dp is, well, this is we haven't figured out what the gradient terms are, but it's the gradient of f times E1 hat and so forth and so on, and then E1 hat H1 du1 and so forth. And if you take the dot product of these two vectors, the orthonormality of the e's give you this expression. And that must equal df. And df, you know, is partial f partial u1 du1, partial f partial u2 du2, partial f partial u3 du3. So equating these two equations, we get that the one component of the gradient is the partial of f with respect to u1, but divided by h1. The two component here is this one divided by h2, and this one is this one divided by h3. And so in general, it looks like that. And for the 3 standard cases, there are actually 11, I think, standard cases. Okay, there's a question here somewhere. Why divide again by h? Oh, we're dividing h here because we're equating these things. So the coefficient of du1 is partial f partial u1, but the coefficient of u1 here is the first component of the gradient times h1. So if we want to know what the first component of the gradient is, it's got to be this thing divided by h1. Anyway, this analysis for the case of the 3 standard coordinate systems in 3 dimensions is like this. And in particular, if you're talking about the gradient of 1 over r, then when you differentiate, what you get is this. And in particular, if you do that in spherical coordinates, then you see 1 over r doesn't depend upon theta or phi, so it's just partial of 1 over r with respect to r times r hat, and that gives you this expression. And if you replace r by r minus r prime, you get this version. So this is an application of spherical, the gradient in spherical coordinates. Now, the divergence of a vector is defined infinitesimally by taking an infinitesimal cube and computing the integral of the vector over the surface of the cube divided by the volume of the cube. And the surface integral of S is of V is the sum of the integrals of V1, V2, V3 over the cube's 3 forward faces minus the sum of the integrals over the 3 backward faces. And so the forward faces for V1 is, well, you're going the sides, the 2 perpendicular sides of the V1 face, the one direction face, in which V1 is pointing out, is du1, du2, but times these scale factors, h2, h3. And similarly, you have to dot, for V2, you have V2, h1, du1, h3, du3 for the 2 face, and for the 3 face, h1, du1, h2, du2 times v3. And then you subtract from that the integrals over the backward faces. And that mean, and so what happens when you subtract? Well, when you subtract this forward face, subtract from the forward face the backward face, you get the difference of V1, H2, H3 over the forward face minus that over the backward face. And that amounts to du1 times the partial derivative of vector u1 of V1, H2, H3. And similarly for the two faces in the forward and backward second direction and the forward and backward third direction. So you get that the surface integral of V is given by, over an infinitesimal cube, looks like this. The divergence then is the ratio of that to the volume of the cube. The volume of the cube is h1, h2, h3 times du1, du2, du3. So this cancels and you get this factor in the denominator, this factor in the numerator. So that's basically our divergence formula. This is a little more complicated than what one normally sees, but it's the general formula for orthonormal vectors in 3-dimensional space. In rectangular coordinates, it's very simple because the h's are all unity, so it's just dv1, du1, and so forth, which in this case is dvx, dx, dvy, dy, dvz, dz. In cylindrical coordinates, you've got to put in, notice you don't put in h1 and you put in the ones that aren't there. So for V1, you put in H2, H3. For V2, you put in H1, H3. And for V3, you put in H1, H2. And you divide by the product. And so doing that for cylindrical and spherical coordinates, you get these expressions, which I think you can work out. Now, if you assemble a suitable number of infinitesimal cubes, you can create a 3-dimensional region of arbitrary shape and volume. And here we're imagining an infinite number of infinitesimal cubes. And the sum of the products of the divergences times the volume elements is the sum of the surface integrals over the faces of the tiny cubes. So if you so in other words, if you multiply by the dVs, the volume element, you cancel the volume element. See, this thing is surface element divided by dV. Multiplying by dV, we just have the outward surface area, surface integral. And so this is the surface integral over the whole, the boundary of the outer surface. In this part, nothing cancels, but over here, you've got, for each cube, you've got an outer face, a forward face, and a backward face. And since the cubes stack next to each other, if you have two adjacent cubes on the faces that face each other, one forward, one backward, the surface integral just cancels. So in this surface integral here, or sum of surface integrals, everything cancels except the outer surface. And so we have this, which is Stokes's theorem, one of Stokes's several theorems. The integral of the divergence of a vector over a volume is the integral of the vector dotted into the surface area over the surface. And although I am going to skip most of the examples today, unless we have time. Okay, your copy of the book says Gauss's theorem. Well, the copy editor may have changed my Stokes to your Gauss. I think it's probably, my guess at this point is, I'm not much of an historian, but my guess is that both Gauss and Stokes invented this theorem. Who did it first? I don't know. I guess the best thing would be to say they probably both discovered it, and just look in Wikipedia and see who lived first, and that's the person I should probably give credit to. And I think that probably is Gauss. Anyway, Gauss discovered almost everything, so it's always safe to call something Gauss's law. In any event, the integral of the divergence of the negative gradient of 1 over r, and the gradient was computed in 2017. There it is on the screen. However small, centered at the origin. Okay, so let's do this. The divergence of this will have to be the surface integral of that. But the surface area here is r squared r hat. And now the two unit vectors just give 1. The r squareds cancel. We just get the integral of d omega over a tiny sphere. But the integral of d omega over any sphere is 4 pi. So that means that this funny thing here, the divergence of r hat over r squared, integrated over any sphere, no matter how small, gives you 4 pi. We could equivalently have done this in rectangular coordinates, and then it would have been the integral of the divergence of the gradient of 1 over r over any tiny cube gives you the area of the cube. In any event, or similarly, the integral of r minus r prime over that cubed over any sphere, however small, centered at r prime, also is 4 pi. I mean, this is just translating this equation to the point r prime. On the other hand, these divergences, this divergence is 0 if r is not 0, and this divergence is 0 if r is not r prime. And I think Dirac was the first to realize how useful and important this was, namely that these quantities, these divergences of the gradient of 1 over r and 1 over r minus r prime, that these were functionals that he called delta functions, and other people called Dirac delta functions. And what's meant by them, they're not actually functions, they're functionals. And they're functionals in the following sense, that if you have any suitably smooth function f of r, the integral of f of r times the divergence of r minus r prime over r minus r prime cubed is 4 pi times the value of the function f at r prime. This assumes that the integral includes the point r prime. So you can picture this divergence as a point in space that has infinite weight, and when you integrate but has infinite weight when r is r prime and 0 weight everywhere else. So you integrate this thing, you just get that value times 4 pi. As I said a moment ago, the Dirac delta function was, I guess, the first example of something called a functional. And a functional is a map from functions to numbers. So a function is, of course, a map from numbers to numbers. A functional is a map from functions to numbers. And this takes the function f, this delta function maps the function f to its value at r prime times 4 pi. Okay, Gauss's law, well, this is so important that I'll just mention the divergence of E, of course, is rho over epsilon 0, the electric constant. So by Stokes's theorem or Gauss's theorem, anyway, the integral of the electric field over the surface that bounds a volume is the charge inside divided by epsilon 0. All right, I don't know whom to give credit to these various things. I thought I was doing it correctly, but I'll look in Wikipedia tonight. I've always thought that what you call something didn't really matter. The important thing was knowing what these different things are. But the result is that I personally forget the names of almost everything, people and formulas, and that's actually a bit of a handicap. So it's good to know what to call things. Anyway, the Laplacian, so this is a new concept. The Laplacian is simply the divergence of the gradient. So we've defined gradient, we've defined divergence. So now we have the divergence of the gradient. And so in orthogonal coordinates, there are two notations at least for the Laplacian. One is a triangle. The other one is grad squared. The most transparent is the divergence of the gradient. So this exactly says what it is. And if we combine the formulas that we had before, you can get this expression. And once again, I wish I knew how to use the whiteboard and project it on the screen for you, because there are, so what I would urge you to do yourselves at home is to take the formula for the gradient, which is back here. All right, so here's our gradient. And then we take this gradient, and then we take this formula for the divergence, and we replace V by this gradient. And with just a couple of manipulations, what we find is that the Laplacian can be written this way. And notice in this case, you might wonder, how come there are three of them here and why are the two down here? Well, it's that we want to if this thing were written as the sum of three terms, the first term would be partial u. First of all, we'd always have the volume out here, but this would be partial u1 of h2, h3 over u1, partial of f with respect to u1. That's what you'd get. And then you repeat that for the other two. You'd have partial with respect to u2 of h1, h3 over u2, partial with respect to u2. And then you'd have partial with respect to h3, h1, h2 over h3, partial with respect to u3. And so what people do is when they have h2, h3 over over h3, they put an h3 up here so this doesn't change. And then you have to have whatever k is, you have to have h3 squared for the case k equal 3, and h2 and h1 for the others cases. In rectangular coordinates, the thing, of course, is much simpler. It's just looks like this, and that's why these notations are used. In cylindrical coordinates, if you take this formula, you get this, which you can rewrite that way, and in spherical coordinates, you can you get this directly. And then, and what's happened in a couple of cases here are that the general thing is r squared sine theta, but over here, the r squared part well, anyway, yeah, okay, the r squared part cancels. Anyway, this is the expression. I've lost track a little bit. And notice there are two ways of writing this term. The first term with respect to r. In particular, you can write it this way or you can write it that way. And when you're doing quantum mechanics problems where you have the second derivative with respect to r in a spherically symmetric Hamiltonian problem, sometimes this one is the better one, sometimes this one makes things easier. Anyway, that's the Laplacian. And now if you take what we learned about delta functions, or delta functionals if we want to be purist about it, it's the divergence of the gradient of minus the gradient of 1 over r. So that is the Laplacian of minus 1 over r. So in other words, we get these expressions. So it's minus the Laplacian of 1 over r is 4 pi delta, and minus the Laplacian of 1 over r minus r prime is 4 pi times the cubic delta function of r minus r prime. This is a little bit long. I think we can do this later if we have time, or we can do it Wednesday, which is tomorrow, of course. Curl. All right, let's get curl straight and define curl, first of all. It's, first of all, the directed area of an infinitesimal rectangle whose sides are two perpendicular vectors, hi ei hat dui and hj ej hat uj duj is their cross product. And we had the cross product rule because these are orthonormal and we've labeled them in a right-handed way. What we have is e hat I cross e hat j is e hat k, and hj hi hj dui duj. We could have written this as a sum epsilon ijk, epsilon hat k, and then all this. Anyway, the line integral of the vector f is, of course, the integral of f around the little around the perimeter, along the perimeter of the rectangle. And so we go in the UI direction. Now in the, and of course, since what we do is we go this way, that way, this way, that way. Now, when we go this way, we have to keep in mind that we're also going that way. And these are infinitesimally different. And similarly, when we go this way, we're going down that way. And so we have to differentiate, we have to take the difference of the line of this line integral with that line integral. So we have dui, duj, and then the change in hj, fj in the I direction. And then we have minus that for the other way. So it's this one minus that one plus this one minus that one, and the signs work out so that it looks like this. Okay, so then what we do is we define, is our definition of the curl is that the curl dotted into the surface area is the line integral. And the line integral then is this quantity here. And the curl dotted into the surface, well, the surface elements are these shown up here. And so the kth component of the curl is what you cancel the du's, and you have curl of f kth component is 1 over hi hj, this quantity here. God, I don't know why the damned mouse is like this. It is really annoying. And so the curl as a vector field then is a sum over ij and k of epsilon ijk, epsilon 1, 2, 3 being 1, and a unit vector in the kth direction. And then we just have this quantity here, 1 over hi hj, and the partial. And this epsilon symbol puts in the minus sign and gives us the two different pairs here. In rectangular coordinates, all the h's are unity, and so we just have that the ith component of the curl is epsilon ijk partial with respect to xj fk. Now, I remember the thing this way, often one uses a sum over repeated indices in other notation, in other words, in which this quantity here implies that we have the sum over j and k. In any event, the ith component of the curl is epsilon ijk partial j of fk. So you see you have I jk there and ijk here. And that's the way I find it easy to remember it in rectangular coordinates, or Cartesian coordinates, which are the ones that we are using most often. We can, since there's an epsilon here, we can rewrite this whole thing as a determinant, and then it becomes a determinant of the h's, the hi fi's here, the hi ei hats there, and the partial derivatives there. And of course, you could have had this row on top and then this one and then that one. That probably would make more sense. Anyway, this is the general form in orthonormal coordinates. In rectangular coordinates, we get this. In cylindrical coordinates, we have that. And in spherical coordinates, we have that. Now here are two useful identities, and I think these are homework problems, so I'm not going to do them in class for you. But if you just remember that epsilon ijk is 1 or -1 or 0, depending on whether ijk is a cyclic permutation of 1, 2, 3, or not. And if it's not, and any index is repeated, it's 0. And if no index is repeated and it's not a cyclic combination, then it's -1. Anyway, if you do the sum over I, what you get is the product of this, the difference of the product of two Kronecker deltas. And this is worth memorizing, actually, if I suppose, although you don't really need to memorize anything. But the way I think of it is you write one ijk and the other one I something else, mn say. And then what you do is you write two deltas, a minus sign, and two deltas, and you write jk first, j here, k there, j there, k there. And then you take the other two and you write them in the order they appear here, mn, and then in the opposite order in the term that has the minus sign. Another identity is if you sum over I and j, epsilon ijk, epsilon ijn, you get twice delta kn. So you can then write that these identities make it easier to compute the curl of a curl. Because what you can do is you say, well, the curl of AI is first the ith component of the curl, but then, so that's epsilon ijk partial with respect to j, so it's the kth component of the curl, but the kth component of the curl is epsilon kmn, the mth partial on the nth component. And then you use this rule here to replace it by two Kronecker deltas, and that pops out and gives you this. The first term being that m is I, but j is n. So and the m and n things commute, and so we have the ith derivative of del dot a. And then this term gives you the j is m. So this then is a Laplacian, and n is equal to I. So it's the gradient of the divergence minus the Laplacian of the ith component. And so it's curl of A is the gradient of the divergence of A minus the Laplacian of A. And Laplacian of something in rectangular coordinates is pretty simple. It's just Laplacian hitting each of the three Cartesian components of the vector. But if you're in spherical coordinates, the Laplacian of a vector quantity, people usually actually use this equation to define it. And they simply define it as the gradient of the divergence minus the curl of the curl. If you now assemble a suitable set of infinitesimal rectangles, you can create an arbitrary volume with an arbitrary surface, and, or rather, I'm sorry, you can create an arbitrary surface, and that surface will have a boundary. And so the curl of f dotted into the surface element is the integral of f around the infinitesimal rectangle. And then when you add these things up, these guys all add as they, however they must. But in this case, in other words, if you have a little square, a little rectangle there and another rectangle there, then the first rectangle will have this integral, the line integral on the right side will go up, and but the square or the rectangle on the right will have on its left side an integral going down. So these two guys cancel. So you wind up only with the integral of f along the perimeter. which is one of Stokes's theorems. But I completely agree with anyone who wants to say that Gauss also invented it, because Gauss was very smart and he invented almost everything that was possible to invent when he was alive. In Maxwell's equations in empty space are particularly nice to look at because you can just write them like this. There's only one constant involved, c squared here. And so you take this equation and you put it here and you get the integral of E around a surface is minus the rate of change of the flux through the surface. And most of the machines in the world use this equation, and they may also use this equation. They probably use both equations. The magnetic flux through a surface is the integral of B dotted into the integral of the magnetic flux around a surface along the perimeter is 1 over c squared times the changing electric field through the surface, and that is the integral of E dot over the surface. In Maxwell's equations in empty space, if you go back and look at them, you can then take the curl of the curl in these two equations, and if you then use the curl of the curl equation, what you find is the curl of E is the gradient the divergence of E minus Laplacian of E. And in empty space, the divergence of E is 0, so you just have the Laplacian of E. On the other hand, Laplacian of E is the gradient of the, is the curl. Let's see, so this one vanished. We've got this one, and we've got, let's see, this was B dot. B dot was the curl of E. Oh yeah, we go over to the left-hand side then. We have that the curl of E is minus B dot. And so this is the curl of minus B dot. So that gives us this term. And on the other hand, the curl of B is E dot. So if you dot that, you get E double dot with a minus sign and 1 over c squared. Similarly, the curl of B is these two expressions. The divergence of B, curiously, is always 0, whether you're in empty space or not, as far as we know. So this is the minus Laplacian of B. On the other hand, the curl of B is related to E dot. You get the curl of E dot. And on the other hand, the curl of E is also related to B dot. And so we have the curl of E dot is related to B double dot. And you combine these two equations, what you get is that the Laplacian of E is E double dot over c squared, and the Laplacian of B is B double dot over c squared. Well, these are the wave equations, which are why light moves at the speed of light through space. Okay, we've got almost a half hour left, so we can do some examples. These are some homework problems, so I'm going to skip those examples. Let's have questions then from students. Does anybody have a question and would like something explained here, or should I just do another example, or perhaps should I just start Fourier series? Okay, so let's have some sort of a statement here from the students. What do you want me to do? Do you want me to explain something in chapter 2 or in chapter 1? Do you want me to do an example that we skipped? Or, okay, which example? And also starting chapter 3 would not be a bad idea. Okay, here's a question. In the derivation of the divergence, why is the first phase such and such? All right, let's look at divergence. Curl. Laplacian. Okay, here's the divergence. Why is the first face such and such? In other words, this equation here, I guess, well, first of all, what are we talking about? What we're talking about is the divergence is the integral, the surface integral over the surface of the cube divided by the volume. Well, the volume is clearly h1, h2, h3, du1, du2, du3. So that part is easy. The surface area, though, is, well, what you've got here is we're asking for the surface, the integral over the surface, the 2,3 surface in the one direction minus the other 2,3 surface. And so the integral over the outer surface is V1, H2, H3, du2, du3. But on the other hand, V1, H2, H3 changes as you go through the cube from the backward face to the forward face. And so this quantity changes by its derivative multiplied by the thickness of the cube, the width of the cube. Similarly, this one has the surface integral, which would be V2, H1, H3, du1, du3. It changes in the u2 direction by an amount that is du2 times the u2 derivative of this. So that's the best thing. Okay, the students got it. Okay, the best thing is to draw a picture of this, which is why I wanted to use use a whiteboard, and I didn't want to use Zoom's whiteboard because my impression is that Zoom's whiteboard takes the whole screen, and well, I'm gonna have to do more experiments with whiteboard to get this straight. All right, how about another question? Zoom does have its own version, but then how do I tell Zoom to use my iPad? That's the question. Um, 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 all right, well, let's skip the whiteboard for the moment. If I can get it straight on Wednesday, I can draw some pictures to illustrate these things. But I imagine that Wikipedia has pictures illustrating all of these things. Any other question? Yeah, you're right that I tried that and I forget what actually happened. So one student is suggesting that. Well, how about questions? Okay, the statement here is share iPad screen. Okay, I'm opening the iPad. What do you mean share the screen? All right, I think maybe until I get this straight, I shouldn't experiment in class time. So let's just go to another question, or shall I start? It wouldn't hurt to start Fourier series, I think. Okay, well, if Ms. Lin wants to explain that to me, that would be very helpful. Right. Well, I can write on the PDF. That's not the problem. The question is how to get that on the screen of the iMac. All right, let's do this after class. Let me talk about Fourier series. The phases, e to the I n x over square root of 2 pi, for integer n, are orthonormal on an interval of length 2 pi, and that's this integral. So the basic idea in Fourier series is this integral, namely the integral e to the minus I m x e to the I n x divided by 2 factors of square root of 2 pi is this expression here. And if you just do the integral, you see if n and m are different integers, then this thing integrates to e to the I n minus m x over n minus m, evaluated at the two endpoints. But if you put in x equal to 0, you get 1, x equal to 2 pi. If this is an integer, you get 1 also. The difference is 0. So if m and n are two different integers, you get 0. If, on the other hand, n and m are the same integers, you're just integrating 1 from 0 to 2 pi, and that's 2 pi. The 2 pi's cancel. And so you get delta mn, which is 1 if m is n. So this is the fundamental integral for Fourier series. And if a function f is a sum of these phases, it's called a Fourier series. So f of x is a sum, n goes from minus infinity to plus infinity, f sub n e to the I n x over square root of 2 pi. So this was something that Fourier invented. And I think when he first invented it, an awful lot of people criticized him, poo-pooed it, and so forth, and said, well, this is just a curiosity. In fact, it's so much more than a curiosity that it's almost it's just an essential part of physics and mathematics, especially physics and engineering. So now, once you have this expression for the function, you now use the orthonormality of these functions, of these phases, to compute this integral, e to the minus I n x over square root of 2 pi times f of x dx. And you substitute for f of x this infinite sum. So we've got this infinite sum here. And then, provided everything converges suitably, you can integrate independently for each nm and then sum up the results. Well, for n not equal to m, you just get 0. For n equal to m, you get delta nm, and so this is just fn. So in other words, when you can express a smooth function as a Fourier series, the nth component is simply the integral from 0 to 2 pi to the minus I n x f of x dx over square root of 2 pi. And what is extremely useful about Fourier series is that they're simple, and it turns out they can represent any function that's square integrable on the interval in question. And functions can be square integral even if they're not continuous. For example, the integral, say, that is 0 from x equal to 0 to pi and 1 from pi to 2 pi, that's square integrable, obviously, but it also has a Fourier series, but it's not continuous. If we use Dirac's notation, we can think of this phase factor here as an inner product of a vector n and a vector x. And so these are the phase factors are the components of the vector n in the x basis. And the orthogonality integral, which was up here, then can be interpreted as the orthogonality of the two vectors, and we can turn that into an integral by writing I, the identity operator, as the integral of outer products of the x vectors. We stick that in there, and then we use this formula, and we recreate that, and we get this. And since these vectors then are orthonormal, we can write them, the identity operator in that vector space this way. Now, you don't have to think about things this way. It's a useful way of thinking about it. The main thing to think about with regard to Fourier series are these three equations. That's the main thing. The expansion looks like this. The coefficients are these integrals, and the phase factors are orthonormal. Those three equations are 90% of what you need to know about Fourier series. The rest you can pick up on the street. So we can, I think, skip that. And but you can use this Dirac notation to do things in a sort of cute way. You say f of x is the inner product of x with the vector f, and you stick in I as a sum of n's, and you get this expression, or that expression. On the other hand, you can write the inner product of n with f, you stick in I as an outer product of x's, and you get this expression. And these various ways also allow you to write the inner product in different ways. You can write it as a sum over n of these inner products like that, or you can write it as gx xf, and that's g of x star f of x. And moreover, the inner product of a vector with itself, you can think of it this way, but for sure, you can think of it this way and that way. So in other words, coming back to this equation, the very definition of the equation, if you multiply this equation on both sides, here you multiply by the complex conjugate of f, and then integrate from minus infinity to plus infinity, no, from 0 to 2 pi. And then on the right-hand side, you have a sum on m instead of n, f sub m star e to the minus I mx over square root of 2 pi, and integrate that from 0 to 2 pi. Using this relation here, what you get is you get this equation in the form this is equal to that. Now, one thing to look at here is that these series are automatically periodic. In other words, a function, if you write a function as a Fourier series, it's automatically periodic in x with period 2 pi. So if you change x here, if you change x by x plus 2 pi, or x minus 2 pi, or x plus 4 pi, or x plus 6 pi, you haven't changed anything, because e to the I n times 2 is e to the 2 ni, and that's 1. Or e to the 6 ni is 1. So you haven't changed the phase factors, any of the phase factors. And so a function that can be represented exactly as a Fourier series is automatically periodic with period 2 pi. On the other hand, so the Fourier series is periodic. On the other hand, you can take a function that's not periodic, you can compute these integrals, you can make this sum, and then you have an excellent approximation to the function on the interval 0 to 2 pi. And so the left-hand side is the function that agrees with the right-hand side in the interval from 0 to 2 pi, but outside the interval, this one remains periodic, and this one can do whatever it pleases. So that's what's, I guess, explained here. That the Fourier series are periodic with period of 2 pi. So even if a function is not periodic, its Fourier series will be strictly periodic. Complex conjugate of the Fourier series obviously looks like this. And sometimes what we do is we say, we change n to minus n, and we do the same sum. And since we're summing from minus infinity to plus infinity, we can either sum of f sub n star or f sub minus n star. And that tells you that the nth coefficient of the function f star is the complex conjugate of the minus nth coefficient for f. And so if the function is real, this thing on the left, this says f sub n of f is f sub minus n star of f. And so for a real function, the nth coefficient of a real function is the minus nth coefficient of the complex conjugate. Wait a minute, the function is real. Oh, I'm sorry, is the complex conjugate of the nth coefficient. So let me say that again then, since it's a little bit confusing. The nth coefficient of the real function is the same thing as the nth coefficient of its complex conjugate because the function is real. But the nth coefficient of the complex conjugate is the complex conjugate of the minus nth coefficient of the function. So now you take this one equal to that, this one equal to that, and you get this rule. So that's actually quite a useful rule. If the function is real, then its Fourier coefficients are redundant in the sense that the coefficients of negative index are the complex conjugates of the coefficients of positive index. You can do some Fourier series by expansion, but I don't know if this is this is just a curiosity. E to the ix is the 1 over n factorial e to the inx. So these are the coefficients of this function. Beats, well, two sines of almost the same frequency, you can show that they are of this form, and that's illustrated by beats. So this is the sum of the two sines of frequencies that are close to each other will have a beat frequency, and the beat frequency is basically half the difference of the two frequencies. I think we can skip that for the moment. The interval, well, I was talking about the interval 0 to 2 pi. You can actually pick any old interval of length 2 pi. So you can go from minus pi to pi. And in fact, that's done about as often as the integral 0 to 2 pi. Or you could pick the integral minus 2 pi to 0. Or you can just take any real number and go from any real number r and go from r to r plus 2 pi. And however you do it, you'll get the same Fourier coefficients if the function is periodic. If it's so that's what that says. That's what this sentence says. If the function is periodic, the integral is independent of the lower limit. On the other hand, if the function is not periodic, well then clearly the behavior of the function on any interval of length 2 pi has no relation necessarily to the function on any other interval of length 2 pi. And so the Fourier coefficients depend on the interval if the function is not periodic. But whether it's periodic or not, the Fourier series always is periodic, no matter what interval you choose. And the Fourier series also is, if the function is not pathological, the Fourier series will always be a good approximation to the function inside the interval that you used to compute the coefficients. So in this case, the Fourier series with these coefficients will be a good approximation to f between r and r plus 2 pi. There's a question then of where you put the 2 pi's, and there you can, the safest thing is to do what I did, namely at in the very beginning, we go back to these basic equations, we expand the function, and we have the phase factors over square root 2 pi. We compute the coefficients by using the phase factors over square root of 2 pi and integrating. That, if you stay with that, you won't make any mistakes. On the other hand, the cost of that is that in these two equations, you have a square root of 2 pi in both equations. And you don't really need the square root of 2 pi. You don't need to have a square root of 2 pi in two equations. What you can do is you can say, well, I'm going to take those square root of 2 pi's and those two equations that I said, remember I said there were three equations that are 90% of Fourier analysis, Fourier series analysis. And you can take two of those three equations and you can write one this way, and then you have, since you got rid of the square root of 2 pi, you have to put it over here. Or you can take the square root of 2 pi from the denominator of this equation and stick it there. So those are two different ways. The trouble is you've got to make sure that you don't switch conventions in the middle of one calculation. Then you get a mistake. That's something that you want to avoid doing. So in other words, you can pick any convention that's convenient. And if you're new to Fourier series, I would say stay with the convention on the first page, which has 2 square root of 2 pi's. It's a little bit cumbersome, but at least you don't have to worry about anything. You don't have to worry which convention you used. Here are a variety of examples, but we only have 2 minutes left, so I think I should stop with Fourier series and ask whether there's a question. So, all right, there's a statement here that there's a typo or an error in the book. In the second edition equation 2.36, 2.36, all right, well, let's go back to, let's get this straight, because if there's a typo in the book, we want everybody to know about it. Well, let's see, I must have changed the equations here. Oh, right here. Oh, okay, in the example that I skipped. All right, so let's think about this. All right, well, we might as well try to do this example quickly then. The electric field is given by this in static problems. So there's no A dot, so it's just minus the gradient of phi. The divergence then is minus Laplacian is rho over epsilon 0. We write the Laplacian in spherical coordinates, we get this. Okay, and suppose we say that phi is A minus rho r squared over 6 epsilon 0. So on the surface of the sphere, the electric field is minus the gradient of the potential. So it's minus the gradient of this. Where's capital R? Oh, right. Okay. So this would be 1 over 3 epsilon 0 minus, oh, there should be a plus here, shouldn't there? I think there should be a plus here. All right, so let me check that 2.36. So it may be that in the copy editor, who actually, one of the nice things about Cambridge is that University Press is they actually care about the content of the books they publish. And they have copy editors who are actually competent in the fields that of the book. And so, right, so, all right, so I will look at this. I think this should be a plus sign, and it certainly should be if we get this equation here. And so let me just look in the physical book, chapter 2. My copy of 2.36 looks like the thing on the screen, and that thing on the screen may be wrong. I tell you what, I'll send, there's no point keeping everybody here on this. I will send everybody an email about this, because, you know, when tracking down a minus sign, you have to write equations and be careful to make sure you get things right. But I think actually that that the student is right. There should not be a minus sign here. All right, let me end the meeting. If somebody wants to, is there? You know what I think I might do? Let's do this. I think maybe on the Wednesday following each, I think I'm going to try to make all the homework done on Sunday. And on the following Wednesday, we have a class that is not on YouTube. During that class, people can ask me about the homework solutions, and I can show the homework solutions there. I'm not sure. So I don't know. I forget what we sort of, somebody suggested a pretty good idea for what to do about the homework solutions. And I forget what it was. So why don't you guys send me an email and as to what you think the best solution is for the homework solutions. I mean, I don't mind telling you guys about the homework solutions, but I don't want written forms of them, especially LaTeX forms of them, to be distributed, because then I can't use them next year and so forth and so forth. All right, so I think we can end this class now. So is there any last question? And, oh, right, I will try to post the homework tonight. I'll post homework 2 tonight. You're absolutely right. I should have done that. I was thinking about it today, but I didn't actually do it. But you're right. Any other questions before I end the meeting? And I think your names are great, although I'm not happy with the name FERPA because I don't like FERPA. I much rather if you called yourself Maxwell or Faraday or Gauss or Euclid or whatever. All right, I guess we're over then. So I'm going to stop the meeting, stop recording. Okay. Goodbye, everybody. Have a nice evening, and I'll see you tomorrow at 5:30 using not Zoom, but the other thing. Bye.